Okay, then let's go ahead. Our main topic, to estimate the probability density function. One is Kullback divergence, and another is a P-Butterstein distance. Okay, what is definition of the probability Kullback-Leibler distance? Okay, for a probability density function, so-called PDF, Qx and Px is all given. Note that the probability density function is defined like this: Px, Qx. Every part is positive. If we compute the probability by defining a random variable, and if we collect summation integral all parts of the probability density function is 1. That is same even if the probability function is different. Anyway, probability function is given, and consider a subset, open subset in Rn. Then a Kullback divergence or Kullback-Leibler distance, or in a physical view, physics called relative entropy, QP is defined by like this. That is definition of Kullback divergence. And if the integral divergence, then we can define that is infinite. So, as I said, that is estimation between two probability density function, or estimate the gap between probability density function. So, if we consider this data, if true data Q is given and estimated P prime X is given, then that is a distance between two probability between true data and estimated data. As I said, if the value is zero, nearly zero, that estimation is very good. Otherwise, it's a little bad. Okay. But remarkable point is that if a distance, when you consider a met distance, clearly that symmetric rules satisfies. But in case of Kullback divergence, even if, or we call Kullback-Leibler distance is asymmetric. That means that this does not hold. So this is not a metric space. In this reason, some people, some others called Kullback, metric distance. Instead of distance, Kullback divergence, or in physics view, relative entropy. Okay. When you consider just the definition, the symmetric property does not hold. Even though, nevertheless, some people call that is a Kullback-Leibler distance, but it does not distance in mathematical. Let's see some properties of a Kullback-Leibler divergence. A probability density functions. A is still an open set. Also, remarkable point is that A is open subset in Rn. We can define that is a multiple integral. However, in this previous proposition, in definition 16.16, 16.17, we can define double integral, multiple integral in measure space. That is probability measure space. This is a remarkable point. So if this joint probability function is given and A is an open subset in Rn, then the value is always positive. Even if this is not asymmetric, but this value cannot be non-negative. If we change the probability function, density function, and if hold 0, two probability function is same function if in open subset in A, every open subset in A. Let's prove this proposition. To prove these two properties, we can introduce an auxiliary function which satisfies minus log t minus 1. if we observe this function, st is always positive, and the solution of this equation is t1. If we consider the graph like this, t minus 1 log t, and if we plot the graph, log t is like this, and t minus 1 is in fact the tangent line at this graph, at the point 1. So, in this reason, that is always, the gap is always greater than 0, or equal to 0 or greater than 0. Okay, so st is always non-negative, and so like the graph is detail like this. Okay, so the solution is only equal to 1. Then if we compute KQP, consider the Quebec library distance. That original definition is written as QX. Okay, but the interesting point is that that function is written as by, instead of logarithm, auxiliary function s comes this definition. Why this hold? If we compute the right part, by a definition of auxiliary function, that is minus log q of p q minus 1. Okay, but because of the logarithm property, that is written as that comes here, p minus q. Okay, log a is written as log a minus inverse, fundamental property of logarithm, and that is written as p minus q, p over q and minus 1. Next, if we apply distribute law, that is, and integral is linear, q 1. That is just 1. But because q is probability density function, so in that case we can written as 1 minus 1. That's vanishing. So that is just the original definition of Kullback-Leibler distance, QP. Okay. So it is equal when instead of logarithm function, substitute auxiliary function that also satisfies. Okay. Then, if we observe this part, Q and S all positive in given domain. So that guy is also positive. So Kullback-Leibler distance is always positive. And to verify second condition, we can assume that this condition, our aim is Q equal to P. But by definition of the Kullback-Leibler distance, that is, but we can see an auxiliary function. Okay. Then that is probability function. So to hold this equation, only way, because S is non-negative, but that guy is positive, so that should be hold. Okay. But the definition of auxiliary function to hold this for first condition, Px equal to Qx is 1, which means that PQ. So the proposition is proved. That is a definition of Kullback-Leibler divergence, but we can generalize the definition by using Radon-Nikodym theorism. As I mentioned, definition theorism 6.15 from 6.13 to 6.15. So, if instead of probability density function, let's introduce mu and nu measures. Also, it is also good a probability measure. More generally, a measures and satisfies absolutely continuous condition. Then Kullback-Leibler divergence is defined to like this. Okay, that is similar to traditional Kullback-Leibler distance